Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll give you a taste for model selection within the multiple regression context. So here we are at the course website. I'll scroll down to Chapter 3, a taste for model selection, and we want this, go ahead and open that PDF file and the R code within RStudio to follow along with this lecture. Here's the PDF. All right, so the model we are interested in is a multiple regression model where we have a response variable y that we want to predict based on k predictor variables. So we've got these other x variables, these explanatory or predictor variables, and they're all in a model together. And the challenge of model selection is which combination of these x's best explain the response in y. That's it. So basically, which of these x's don't contribute very much, conditional on the other x's being in the model. And we're going to look at several automated methods for selecting these subset models. And the first step is always to plot the data. In particular, plot the response against each of the other predictors to see whether there's curved relationships there, and if so, consider including those transformations in addition to the original x. So say looks like x1 maybe needs a log transformation, you perform the transformation, you plot log x1 versus y, and you see that you have something more of like a straight line. In that case, include both x1 and log x1 as variables or candidate x variables in the model. We're going to primarily look at backward selection or backward elimination, where you start with the full model, which includes variables x1 all the way up through xk. So you've got k variables. And remember, each of these x's, for example, xk could be log x1. All right, this is just a way of enumerating the predictors that are in the model. So the main idea is that we start with a full model and perform all the diagnostics on the model to see that the model fits the data well. Then we ask the question, is there a more parsimonious model that also predicts y very well and still fits the data, and thereby reducing some redundancy of what these x's, which x's are in the model. And so we fit this full model, calculate r squared. This is one strategy, and that tells you something about the predictive ability of the model. And then the backward elimination part is fit k separate models. Each of those reduced models has one of these x's removed. So the first reduced model will have all the variables except for x1. The second model will have all the variables except for x2, and then all the models except for all the variables except for x3, and so on, all the way up to remove xk from the model. Then calculate r squared for each of those reduced models and ask which of these reduced models reduced x squared the least. That's the variable, okay, say it was xk, that was basically the least important, conditional on all the other variables being in the model for predicting the response y. And so let's get rid of it. Now we can continue to do that procedure. Okay, so once we decide which one is going to be removed, and for argument's sake, let's say it was xk. If we remove xk, this becomes the new full model. We've got all the x's up to xk minus 1, and now we assign that to be the full model, and then we iterate. We go round and round. But then we need a reason to stop. And there's lots of ways of selecting a stopping criterion. One strategy is simply to, in the multiple regression coefficient table, let the alpha, or let the p-value that's, if all the p-values are smaller than 0.1, stop then. And basically that allows the computer to make some quick decisions for you to get down to a fairly reduced model, but then you get, as a human, get to make some final decisions about which terms continue to remain in the model. One side note for epidemiologists who use certain selection criteria to perform sampling from a population, if you include certain variables as criteria for sampling certain values, like age and sex and things like, and race perhaps for sampling, then we often include those in the model regardless of their significance as confounding variables. So there are some special cases where you don't simply want backward selection to blindly remove all the variables, but maybe there's a small subset of variables that remain in the model regardless. That brings us to maximum likelihood and Akiki's information criterion, AIC, and the Bayesian information criterion, BIC. These are both criteria for helping us choose between models. And these are the equations right here for the two criterion. So AIC and BIC, those are just numbers that we're going to use for selection. L is a number. It's the maximized value of the likelihood function. So L comes from the likelihood function. And K is the number of parameters in the model. And for both of these, the smallest value wins. So basically, you could imagine fitting all possible models and choosing the best model based on the smallest AIC. All right, so for the likelihood value, I just want to explain the likelihood very briefly. This is one of the few times this number appears in this course explicitly. So the likelihood value, or the maximized likelihood value from the likelihood function. So the likelihood function is a probability function that explains how likely data is conditional on parameter values. Okay, for us, let me page up for a moment. Our parameter values are these betas. Okay, and we have data that are the y's and the x's. And so, so the likelihood function gives us a way of selecting beta values that make the data that we observed most likely under the model. So this is the model. So under this model, which, we have certain data, and the betas that we estimate are the ones that make that data most likely. Okay, so that's why it's called the likelihood function. And the maximum likelihood means that we found those betas that make the data the most likely under that model. All right, so we let the computer do that for us to find that likelihood value. And then we've got this penalty, so the smallest value wins. So we have a likelihood value. We take the log of the likelihood for theoretical reasons, and we multiply this by -2. So -2 is going to make this a negative value. So the higher the likelihood value, remember we want to maximize the likelihood function, so we want L to be the highest it can be. If we take the negative of it, that's going to make it the lowest. All right? So the best likelihood value gives us the lowest AIC, plus a penalty. So this penalty, this K is the number of variables we have in the model. So if we only had one variable, one x, like in simple linear regression, we have a small penalty here. We calculate whatever this value is, and then we're going to add 2 times 1. So we're going to add 2. If you have 2x variables, then you've added 4, and so on. So there's a balance here between the quality of the model fit, which is measured by the likelihood value, and the number of parameters or the complexity of the model. So the more parameters you have, we end up with a larger penalty. So this part wants the model to be simple, while this part of the likelihood wants the model to fit the data well. So there's that balance. And the only difference between these two equations is that penalty term. AIC is just 2 times the number of parameters, and BIC is pretty similar. Notice there's a K there. It's just this number here. So in the AIC, this number is 2. In the BIC, this has to do with the natural log of the sample size. So let's see, if I just brought up R for a second and brought up the console and did EXP of 2. So if you had a sample size of around 7 or 8, the log of 7 or 8 is roughly 2. So if you have a sample size that's larger than 8, say, 8 or larger, then we have the log of that is larger than 2, so we have a bigger penalty here. So with larger sample sizes, the BIC is going to penalize more for large models. So if you use BIC, you will tend to have a more parsimonious model, meaning you'll have fewer terms in it, whereas AIC is a little more liberal and will allow more terms in there. So that's the idea here. We want a good model fit from the likelihood function, but we don't want it to be very complex, so we'll penalize for the number of terms. All right, so we'll see how that works in a moment. Oh, this is a good point. I've been focusing on the beta, but another parameter in the model is the variability of the residuals, sigma squared. So those are all the parameters in the model. All right, I basically said what all of those paragraphs say. All right, so on to our example, the Peru Indian blood pressure. So recall from the last chapter that we have Peruvian Indians living at high elevation. I'll just simply say sort of on the mountain. And at some time in their life, they move to the valley. They move to a lower elevation. And we want to understand how that affects their systolic blood pressure. We created a variable last time that has to do with the fraction of their life that they lived at the valley. Okay, so if they were a 40-year-old individual who lived 20 years at altitude on the mountain and then moved to the valley and lived 20 years down there, that fraction down in the valley would be half. I should have picked a better example. So if, say you're 40 and you lived 30 years on the mountain and 10 down in the valley, then your fraction at the valley would be 25%. I believe that is, I think it's actually the other way around. Years since migration divided by age. This is how old you are when you migrated. This is your current age. This is the proportion of your life you spent on the mountaintop. Okay, so I had that background backward before. All right, so we'll read this data in from the website, create this new variable, the year age variable, and I'm just going to pick a subset of the variables in this data set I've got systolic blood pressure, weight, and height. Then we have 3 skin fold measurements, the chin, forearm, and calf skin fold measurements. Basically, they have a caliper, or sort of a pincer that measures, and you pinch the skin between the caliper, and then you measure how wide that skin fold is. It basically tells you how much fat there is in the skin. This is your resting pulse rate, and then the year age, the year proportion that you spent in at high elevation. All right. Another thing that using the subset variable does, or subset function, is it allows us to reorder these variables so that systolic blood pressure is now the first column in this data set. All right, so I've assigned this to Indian 2. That's the data frame name. All right, so we're going to use galley to create a scatterplot matrix of these variables, and I've selected to put the points, the scatterplot, in the upper triangular matrix of the scatterplot, and then values of the correlation on the lower part. So we'll see the plot right now, and I'll zoom out a bit, which makes it too small to see, but we'll get the big picture. So on the diagonal of this matrix, we have smoothed density histograms of each of the individual variables. In this top left corner, we have systolic blood pressure as a row, and as a column, we have systolic blood pressure here. Okay. When I indicated points on the upper triangular matrix, that's the upper triangular is in the upper right-hand corner, and the lower triangular has the correlation values, which I specified as lower. So this gives us all the pairwise scatter plots for all pairs of variables. The top row says how each variable relates to systolic blood pressure. So we see a positive relationship here. The second column is weight. And we see some other sort of positive relationships. We see a negative relationship here, maybe a negative relationship here. And then we see in the other plots, let me zoom out just a little bit more, the relationship between the x variables. In particular, let's see, all the skin fold measurements. So the chin skin fold measurement, along with the forearm measurement, that's this plot here. There's a positive relationship there. Chin versus calf is here. There's a positive relationship here. And down here, this is the forearm and calf. Those are all positively correlated. And if you want to look at what the correlation value is, go to the other side of the plot across the diagonal. This correlation here is 0.736. Very small number in point size, but actually a large correlation. All right. This correlation, for example, if you go to the other side of the plot, is 0.516. So we have some x variables that are correlated with each other. So my suggestion earlier was to plot the data and ask whether there's any obvious transformations to be made. And looking at the pattern for the response variable systolic blood pressure versus the others, I'm not seeing anything obvious here. There are two observations here that seem unusual to me. For example, if you look along this weight row, okay, there's one observation, this one here, that really stands out. It's someone with a much higher weight than the rest of the folks. That's the same as this point right here. So they have a fairly high weight and are on the high side of the systolic blood pressure. There's another observation here, which I think is a bit unusual too, that this is a very high systolic blood pressure relative to the other people in this study. So we want to be aware of these unusual observations because they may have undue influence on the model fit and thereby they will also influence the model selection and what combination of X variables we end up with. We may want to perform model selection with these observations, and then try to remove them and see what model selection results in after that. You know, what I would do as a scientist is I would go back to the data collection and I would ask, why is this number so large? Was it a recording error? Was this value of like 88 or whatever, was that supposed to be 68 and it was just recorded incorrectly? Okay, so let's see, weight and height. Weight versus height, that's this. So this person is much heavier relative to other people of the same height. All right. So just maybe to remind us that we can use this miscellaneous package to look at a correlation matrix and to do a set of hypotheses tests for whether the correlation equals 0 or not. So these numbers are the same as what were in the plot above, correlation values, in particular, say the skin fold, the chin versus forearm and calf and forearm, those are all fairly highly correlated, between 0.5 and 0.7. And in the table below, we have p-values for testing whether the correlation is equal 0 or not. And we reject that null hypothesis in all those skin fold cases. For systolic blood pressure, we find that weight individually is highly correlated, but really not much else. In the previous chapter, we saw that year age was something that was not significant by itself, as we see here, but when you pair it with, I think it was weight, we saw an important relationship there. All right, on to the model selection. So, first fit, the full model. So I'm going to call this, I try to call my linear model objects by useful descriptive names so I can keep track of what's happening. So here I'm going to fit the linear model, the y variable systolic blood pressure related to all the other variables added together in the Indian 2 data set, and I'm going to call that my full model. Okay, so I put LM because I'm getting this from the LM function. Indian 2 is the data set name, and full is the full model. You can call this anything you want. I'm just naming it that for myself. All right, so I'm going to scroll down actually to the summary table. Okay, so here's a summary of that model. And when you've got all the variables together, we see that weight is significant, year age is significant, conditional on all the other variables in the model, but nothing else is right now. Now remember our phrase from last time, everything depends on everything else. It is possible that, okay, so if we find here the least significant variable, calf, that if we remove this variable, that suddenly everything else becomes significant, or nothing becomes significant after that. It's hard to know beforehand how what will change in terms of significance when you remove or add a variable to a model. All right, so here we've got r squared 0.5259, okay, so almost 0.53. I think I basically said all that stuff. All right, so now I'm going to manually show you how to remove variables using the update function to perform model selection. So if I scroll up again just for a moment, okay, we have the largest p-value here is 0.8, and that is for the calf variable. So that suggests that we can remove calf, and that will cause the smallest change in R squared, the smallest reduction. Okay, so here we are. I'm going to start off by assigning the full model to red for the reduced model. And I'm going to reuse the reduced model until I'm done. Okay, so here's the reduced model that has all the variables in it. I'm going to update that model by subtracting the calf variable. And notice there's some symbols here. So there's the tilde, there's a period, and that period basically is standing in for the entire model with all the variables. And from that model, we're going to subtract calf. That becomes the new reduced model, and then I'm going to ask for the summary of that model. So let's see what changed. Notice that calf is no longer in the variable list. Weight and year age are still significant, but nothing else at, say, a 0.1 level. And the next largest p-value is 0.7. Let's see where how the R squared changed. The multiple R squared dropped from, now I need to page up because I don't remember numbers like that, 5259 down to 5255. Wow, it changed the fourth decimal point by 4 units. So not a big deal. By calf, we're happy to have you gone. So the next biggest one is 0.7. That's the pulse rate. And so I'm going to do the same thing. I've got my reduced model. I'm going to subtract pulse from it, update that reduced model, and ask for the summary. And we're going to go from 5255 down to 5234. Small change. All right, what's the next loser? Forearm. So we'll remove forearm, update that, look at the summary. We'll go from 0.5234 to 5207. All right, chin is getting close to significant here. Height is not, though, and that's the largest p-value, so we'll remove height, and we'll go from 5207 down to 5033. Notice chin now stopped becoming significant. So chin was actually more significant when height was in the model. All right, but chin is not significant at the 0.1 level, so we'll remove chin. And finally, we have a model where everything is significant at the 0.10 level. Our multiple R squared dropped down to 0.47. It started at 0.524 or something. So we lost some explanatory power, but we had, what do we have, 8 variables in the model before when we started? Seven. Our first full model had 7 variables, and explaining the relationship, the predictive model with all these variables in it is fairly complicated. However, once you've finished model selection, now we have a fairly simple model with only 2 variables. We don't make predictions quite as well as we did before, but we have gained a lot in the ability to have a simple model that's easy to explain. And so there's that trade-off. So finally, I'm going to assign my reduced model variable to an object called final, and then I might work on all my diagnostics and interpretations based on this final model. This strategy of having these 3 object names allows me to know where I started when I had the full model, allow the reduced model variable to capture all the changes that I make, and then the final is the one that I end up using for all my analysis at the end. All right. So let's see how this works in an automated fashion, right? I had to make all the manual selections when I was using the update function, but that was a lot of work. So let's make it easy. So we'll use either AIC or BIC for this, and there's a function called step, which will automatically perform this stepwise regression. In particular, backwards selection is the type of stepwise selection we're going to look at. So at each step, the predictors are going to be ranked from least significant to most significant, and then the decision about whether to keep that top least significant predictor will be made. And the one, so okay, I'll make some comments when we see the output. So here is our full model, and I'm going to do stepwise selection. The direction is backwards, so we're going to start with the full model and reduce. And this test equals F just creates a column that shows the results of the F test. That is the p-values that we saw in the table above. The default here is that stepwise is going to use AIC, okay, which gives often very similar information to the p-value approach that, or the F-test approach that I modeled or showed you pages above, but sometimes it will vary just a little bit. If we want to use BIC, we have to include an additional option here that says k equals log n row of the data frame, so that the penalty by default is k equals 2, and if we want BIC, we just set k, that penalty, to log of the sample size, which is the number of rows. All right. So we're going to scroll through a bunch of output. I'll describe the first one or two, and then I'll scroll through pretty quickly. So with the full model, right here, the AIC value is 186.6. That means the negative 2 times the log likelihood plus 2 times the number of predictors, 2 times 7, so okay, so you added 14, gives us the number 186.6. Now these are ranked by the least significant variable, calf, down to the most significant, weight. And you can see that in the p-values for the F statistic here. You can also, the sorting, however, is done based on AIC. So this column is really where the model selection that is the model selection criterion that's being used. So here we have the largest AIC. That means that if we were to remove weight right now, the AIC goes from 186.6 up to 203.7. And remember, the smaller AIC is the better AIC. Whereas if we remove calf, the AIC increases a tiny bit, but not that much. Okay. None is the current value of the AIC. So 186.6, that's this number here. So that's what happens if we do nothing. That's the current model. And so we actually make improvements in AIC. Notice the AIC gets smaller if we drop any of these, whereas it gets larger if we drop any of these. So the reason that is because the penalty is stronger than the likelihood portion of that equation. All right, so because calf is bad, conditional on all the other variables in the model, we will remove it. So you can see right here we've got the next step. Calf is not in there. Here's the AIC value that we had when we were removing calf. And so this none is now this new model. Okay. And now, given that calf is removed, pulse is the next one that we can move. And basically anything that's above this none line is probably worth removing. But we do it one at a time because everything depends on everything else. So we remove pulse. That's why in the next step we don't have pulse. And now I'm going to start going a little more quickly. So remove pulse. The next one is to remove forearm. Then we remove height after that. And this is where AIC stops. When none rises to the surface, there's no more variables that we can remove that will improve the model based on AIC. Notice that this model included chin in addition to the other two, even though, say, at a 0.1 level, the p-value is not significant. So AIC can choose a different model than using p-values from the F statistic. That will choose a different model from BIC. There's all these different choices to make. Which one is correct? None of them is the answer, but each of the many of these methods can be useful to help us choose at least getting down from a full complicated model to a smaller parsimonious model, and then we can make good decisions after that. All right, so if you want, you can do the BIC just by putting this additional option in there. And there's some additional remarks here. In particular, the R-squared decrease is what we saw before. We started around 0.53, and it decreased after a number of iterations down to 0.47. Not a big deal, but we had a much simpler model after that. All right. Finally, once you get down to a reduced model, and here I'm just going to include weight and year age as my reduced model, you want to make sure you do all the diagnostics for it. So, all right, here's our summary of the model. We have a positive relationship when we increase weight. We have by 1 unit, so 1 kilogram, we have an expected increase of 1.2 units in the systolic blood pressure, whereas for every full life increase in year age, we have a decrease of 26 for systolic blood pressure. Basically, for every 10th of your life that you additional that you live down at the valley, you have your blood pressure decrease negative 2.6. All right. All right. So let's look at the diagnostic plots. There's some comments above that show this. First of all, we have a huge Cook's distance for observation number 1. That's probably that's worth noting. We see that sort of a large value in the residuals. Observation 1 is also up here. Okay, so it doesn't have high leverage, but it does have high influence. So we want to be sort of aware of that. It's this point right here. There's another point that has high leverage because of the high weight, but didn't have high influence. That's this observation here again. Okay. So recall that the added variable plots show us how variables relate to each other after adjusting for all the other variables. So what's the relationship between systolic blood pressure after controlling for year age with weight after controlling for year age? And we see that number 1 really stands out here. It's really unusual. So we may want to redo all the work that we just did. Of course, it's automated, so that won't take that much time. After we remove observation 1, it will show us whether our conclusions are highly influenced by this one observation, or maybe our conclusions remain the same, even with it in there. Same thing over here with year age. 1 seems to be an outlier. Otherwise, there's a nice positive relationship here. In both cases, there's no really unusual pattern. Observation 39 seems unusual in this plot, but it's not a standout over here. So, this is where data analysis becomes more of an art, where you want to make reasonable decisions to make the best conclusions about the population that you can. All right, go ahead and read the rest of the description there, and I'll come back in part 2 to discuss this other interesting data set, Dennis Cook's rat data, which shows how valuable diagnostics are.